Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the Humanal University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we'll talk about neural networks. So the so-called convolutional neural networks, they are like cascaded filter banks, but they have a nonlinear function at the output of each filter and a constant offset. And you can read more about convolutional neural networks here in this tutorial from the internet. The coefficients of these filter banks, or when we're talking about neural networks and we are talking about weights, so the coefficients, they are called weights. In this the so-called neural networks, they simply use a weighted sum instead of convolution. So these are, for example, in a fully connected layers or dense layers. Instead of using convolution, they are the simple neural networks. So there are many different architectures, and we are going to focus just on fully connected layers and convolutional layers. And you can read more about artificial neural network here from Wikipedia, and also on this book, An Introduction to Neural Computing. Just an example of an application. You can take a look here on this work from Stanford. And it's a nice application for image understanding. So all these types of neural networks, they use several layers of cascading. When there are more than 3 layers, they are called deep neural networks, or they're called also the deep learning. So these are very current active research areas, especially, for example, in speech recognition, image recognition. And a very popular example is the MNIST handwritten digit recognition, described here on this tutorial from Machine Learning Mastery. And the handwritten digit recognition using convolutional neural networks in Python with Keras. So we will talk more about convolutional neural networks. We will talk more about Keras and other alternatives to Keras and other libraries. So this example, as most neural network implementations, they use Python, and here it's using the library Keras, which is a library that is built on top of other libraries such as TensorFlow or Theano, that used to be used in the early days. And another is very popular, also is PyTorch. Each library has its own pros and cons. Keras is a bit easier to use, and you can achieve faster results for more simple models. But it also offers less resources to the inner code. TensorFlow and PyTorch, you can have access more easy to different parts of the mechanisms, but Keras is a great library for starting and to have fast prototyping of models and trying things out. But in this course, we're going to take a look at Keras using TensorFlow and in PyTorch. So, as we said before, there is a nonlinear function in the output of the filters in a convolutional neural network, or there is a nonlinear function also in these neurons, and they are also called the activation function, and one of them is the so-called sigmoid function. So this sigmoid function is a function that has this S shape and is given by this formula here. So it's defined by 1 divided by 1 plus e to the power of minus x. And we see that we don't have negative values. It goes from 0 to 1. And we can also plot this function in Python. We have the sigmoid function here. So we see that it behaves like a soft limiter function. So the derivative of the sigmoid function is given here. And it's the e to the power of x divided by 1 plus x e to the power of x squared. And this is one activation function, and there are other activation functions. For example, popular ones are the hyperbolic tangent, the 10H, or the ReLU, is the rectified linear unit. And in this case, the ReLU will return x if x is greater than 0, and alpha times x if x is smaller than 0. We also have different types of ReLU depending on the value of this alpha. So this alpha can be 0, this alpha can be a predetermined slope, or it can be some value. So then we have leaky ReLU or parametric ReLU. So there are different, and we also have other activation functions. So we can see here in Keras we have here many different types of activation functions. So we have ReLU, we have sigmoid, softmax, soft sine, hyperbolic tangent, the scaled exponential, linear unit. So depending on the application, we can choose different activation functions. In the following diagram, we'll see a 3-layer artificial neural network. And we have here, we have input layer, we have hidden layer, we have an output layer, and here we have our outputs. So here we have our weights, we have our nodes or our neurons. In this example, we are using the sigmoid functions. So the values with index 0 are often assumed to be the biases. So they're fixed values. In general, we have several outputs in our neural network. So output k is the nonlinear function of a sum given by this here. So the sum is the weighted sum from the hidden layer outputs h of j. So if we choose x0 equals to h0 equals to 1, such that we obtain a constant offset as part of the sum. We get this here. Then the output of the hidden layer hj is again a nonlinear function f of a sum of hj. So we see here that we have our inputs, and then there is this weight, and then we have our hidden layer, and then we have weights again, and we can have many hidden layers here, but we have our output layer, and then we have our output, and we see that the output is given by this sum, and also the output of each hidden layer is also given by this sum from the inputs, and we have these weights. So the output of our neural network depends on the weights w and the inputs x. So here we are assuming a fixed sigmoid function. So if we assemble the inputs into a vector x, which contains all the inputs, and a vector w, which contains all the weights from the hidden and the output layer, then we can express the dependency, and then we can rewrite the output k. So output 1, output 2, output 3, and so on. Output k as O k x in w. So this is the output k. So now we would like to train the network, meaning that we would like to determine the weights such that if we present the neural network with a training pattern in x, the output produces a desired value. So for instance, if we present an image with an object in it, and the output indicates that the object was there with a desired output value. Hence, we have training inputs and we have desired outputs. So we will express d of k, and these desired outputs are also called the targets. Then we now use some optimization algorithm to update the weights w to obtain the outputs O of k as close as possible to the desired outputs d of k with a given input x. So what we do is we will have our desired output, we will we'll feed the network with some input. Then we have the multiplications and summations with weights depending on the number of hidden layers, and then we will get these outputs. We want that this output is as close as possible as a desired output, and then through some optimization we will adjust the weights, and we'll keep doing this until we have that the outputs of our model is as close as possible to our desired output.